Finding the equation of a plane through 3 points. Suppose a plane goes through the points P with coordinates P1, P2, P3, Q with coordinates Q1, Q2, Q3, and M with coordinates M1, M2, M3. Then we want to find the equation of this plane. It's pretty easy to do so because we know that the plane is parallel to the vectors, for example, PQ and PM, and that it also goes through the point P with coordinates P1, P2, P3. Obviously, it doesn't matter which vectors you choose. You could also choose QP and say QM and let Q be the initial point, but the way I've drawn it here, I've chosen P to be the initial point. Anyway, it says find the vector and Cartesian equations of this plane. Alright, let's go ahead and find the vector equation first, because that one's much easier. So, remember, we said that the vector equation of a plane looked like this. So first we need an initial vector, one to actually get us onto the plane. So in this case, we can take OP. So we need an arbitrary name here. So R of, say, T and S, where T and S are real numbers that we're going to allow to vary. So R of T and S is equal to the vector OP plus T times some vector that the plane is parallel to, for example, PQ. So T times PQ means we can go any distance in this direction that we like. And then plus S times the other vector that the plane is parallel to, which is PM. So once we've gone wherever we like in the PQ direction, we can go wherever we like in the PM direction. So that allows us access to all of the points on the plane. Okay, and since P has coordinates P1, P2, P3, Q, Q1, Q2, Q3, and M, M1, M2, M3, it's pretty easy to write this thing out now. We know that OP, the vector OP, is equal to the vector P1, P2, P3. The vector PQ is equal to OQ minus OP, which is equal to Q1, Q2, Q3 minus P1 minus P2 minus P3. And we also have that PM similarly is equal to M1, M2, M3 minus P1 minus P2 minus P3. Alright, so that means that our vector equation R of TS is equal to P1, so this is OP, P1, P2, P3 plus T times PQ. So Q1 minus P1, Q2 minus P2, Q3 minus P3 plus S times M1 minus P1, M2 minus P2, M3 minus P3. Okay, so that's our vector equation of the plane. As for the Cartesian equation, I think I'm going to cop out a little bit here and say let's come back to this one later. I haven't tried, but I guess you could do some really complicated thing here and solve for x of ts, y of ts, so z of ts. So, I mean, from here, I guess, yeah, you can just observe that using the last two equations, these are linear equations about y and z in terms of t and s. So, using equations 2 and 3, so using 2 and 3, you can find t and s in terms of y and z, and then substitute into 1, and that will give you an equation of the form ax plus by plus cz equals d. Although I do admit it's a bit of a nightmare with all these letters flying around. Let's go ahead and do it real quick. You don't have to watch this if you don't want to. You can stop the video here. But I'm just gonna relabel everything and prove that you do end up with something like this. So instead, let's change equations 2 and 3 to make it look like this. So I'm gonna make this one here a11 and this one here a21, etc. So let's change it to a matrix equation. A11, A21, A12, A22 times the vector TS, and then P2 is going to be A13, and P3 is going to be A23. So I'm going to bring those over to the other side of the equation. So that will give me the vector Y minus A13 and Z minus A23. And so from here we get that T times S, sorry, not T times S, T and S. Well, let's take matrix inverses of both sides of this equation. So let's say that the inverse of this matrix is B11, B12, B21, and B22. So that's the inverse of this matrix here. And then times Y minus A13 and Z minus A23. I'm being real lazy here, but remember my goal was just to show that we end up with an equation of this form here where A, B, and C are real numbers and D is a real number as well. And then from there we can then just observe that T is going to equal, well, B11 times Y plus B12 times Z minus B11 times A13 minus B12 times A23. So in particular, T is just going to equal, let's say, C1 times Y plus C2 times Z plus C3, and similarly S is going to equal, let's say, D1 times Y plus D2 times Z plus D3. And so finally, we know that T and S are linear equations of Y and Z of this form. And so when we substitute them in here into equation 1, we have P1 times some linear equation, or times some linear value of Y and Z times Q1 minus P1 plus some linear value of Y and Z again times M1 minus P1, and that's just equal to X. So of course that's going to simplify down to this equation here. Thankfully though, we don't have to do it. Do it this way. There's way easier and less time consuming ways to do it. Although when we have actual numbers instead of like M1 and P1 and Q1 and P1, it's going to be easier and faster anyway if we wanted to do it this way, but we don't have to do it this way.